September 12th, 1942. 43,000 feet above Southampton. Flying Officer Emanuel Galitzine felt the frozen air bite through his oxygen mask as he watched the German bomber materialize through the thin atmosphere like a ghost. The Junkers Ju-86R floated at an altitude where no British fighter had ever intercepted before, where the air was so thin that conventional engines simply stopped breathing, where German bombers had been attacking England with complete immunity for weeks. Galitzine's stripped-down Spitfire Mark 9, converted in desperate secrecy at Rolls-Royce's Hucknall plant just days earlier, carried no armour, no guns except 2 cannons, nothing that wasn't absolutely essential for this impossible mission. But buried beneath its cowling sat something revolutionary. 2 superchargers, stacked in series, compressing air with a violence that physics textbooks said was impossible. As Galitzine pushed his throttle forward and felt his aircraft accelerate where it should have stalled, as he watched the German pilot's shocked expression through the perspex, he realized that one mathematician's stupid obsession with mismatched impellers had just rewritten the rules of high-altitude warfare. The autumn of 1941 brought a crisis that threatened to unravel everything Britain had fought for. Reports flooding into RAF Fighter Command painted a picture that senior officers refused to believe. Pilots returning from combat over France spoke of a new German fighter that made their beloved Spitfire Mark 5s feel like training aircraft. The Focke-Wulf 190, nicknamed the Butcher Bird, had appeared in the skies over northwestern France in August 1941, and within weeks it had transformed the air war into something approaching a massacre. Air Marshal Sholto Douglas stood in his office at Fighter Command headquarters, reviewing combat loss reports that made grim reading. In the first week of September, alone, his squadrons had lost 17 Spitfires over France, while claiming only 4 German aircraft destroyed. The mathematics of attrition were brutal and undeniable. At current loss rates, Fighter Command would lose its offensive capability within months, forced back into the defensive posture that had nearly cost Britain the Battle of Britain just 1 year earlier. The captured intelligence reports were even more disturbing. When Oberleutnant Armin Faber mistakenly landed his Focke-Wulf 190A3 at RAF Pembrey in Wales in June 1942, the subsequent test flights revealed the full magnitude of British inferiority. At 2,000 feet, the German fighter was 25 to 30 miles per hour faster than the Spitfire Mark 5. At 3,000 feet, the gap widened to 35 miles per hour. Most devastating of all, the Focke-Wulf could outclimb, outdive, and outroll the Spitfire at every altitude. British pilots could still turn tighter in a dogfight. But the German pilots could dictate when and where combat occurred, engaging when they held the advantage, and disengaging at will whenever the situation turned against them. Squadron leader Douglas Bader, one of Britain's most experienced combat pilots, described the tactical reality with characteristic bluntness. The 190 can outrun, outclimb and outdive the Spitfire, he reported after flying against the captured German fighter. We can outturn it, but you can't turn all day. The implication was clear. British pilots were being forced to fight defensively in what was supposed to be an offensive campaign over occupied Europe. The Luftwaffe had regained air superiority through superior technology, exactly the situation Britain had feared since the dark days of 1940. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crisis came to a head during Operation Jubilee, the amphibious raid on Dieppe on August 19, 1942. 48 squadrons of Spitfires, most equipped with Mark 5 Bs and Cs, flew in support of the ground assault. Against them, the Luftwaffe deployed primarily Focke-Wulf 190s from Jagdgeschwader 2 and 26. The resulting air battle produced casualty figures that shocked even hardened RAF commanders. 90 Allied fighters were lost compared to 23 German aircraft. The Butcher Bird had lived up to its name, and Fighter Command's offensive operations over Europe ground to a near halt, but 20 miles south of Derby, in a cramped office at Rolls-Royce's development facility, a young mathematician named Stanley Hooker had been working on a problem that most senior engineers considered already solved. Hooker had joined Rolls-Royce in January 1938 after Ernest Hives, the company's general works manager, had made a deliberate decision to bring in technical staff from outside the insular world of traditional automotive engineering. Hives worried that Rolls-Royce was becoming too isolated, too reliant on conventional thinking that had served them well in peacetime but might prove insufficient for the coming war. Hooker was an unusual recruit, an Oxford graduate in applied mathematics who specialized in fluid dynamics and aerodynamics. He had been working at the Admiralty when Hives interviewed him. Unlike the mechanical engineers who dominated Rolls-Royce's design departments, Hooker approached problems through mathematical analysis rather than intuitive mechanical understanding. When he arrived at the company's Derby facility, Hives gave him unusual freedom. "Spend a few months looking around," Hives told him. "Find something interesting to work on. Learn how things operate, then make yourself useful." Hooker wandered through the factory for weeks, observing engine tests, studying technical drawings, asking questions that sometimes irritated veteran engineers who considered their methods beyond criticism. He eventually found his way to the Supercharger test section, where engineers were recording performance data on the Merlin engine's compressor. The Supercharger, mounted at the rear of the Merlin, was a centrifugal compressor that forced air into the engine's cylinders at pressure, allowing the engine to maintain power at high altitudes, where the thin atmosphere would normally starve conventional engines of oxygen. The test curves fascinated Hooker. As a fluid dynamicist, he recognized the plots as aerodynamic performance data, familiar territory for someone who had studied how air flowed around obstacles and through confined spaces. He asked to borrow a set of test curves and spent several days familiarizing himself with supercharger theory, reading everything the company library contained about compressor design and performance optimization. What Hooker discovered troubled him. The Merlin's supercharger achieved respectable performance, certainly better than most contemporary designs, but the efficiency numbers suggested fundamental problems with the system. The rotor and diffuser appeared to be mismatched, working against each other rather than in harmony. Worse, the supercharger's location at the rear of the engine created a tortuous path for incoming air, with multiple bends in the intake ducting that destroyed smooth airflow and created turbulence that reduced compression efficiency. The senior engineers at Rolls-Royce were not impressed when Hooker shared his observations. The Merlin supercharger had been designed by experienced specialists who understood the mechanical constraints of mounting a high-speed compressor on an aircraft engine. The layout was dictated by packaging requirements, manufacturing limitations, and the need to integrate the supercharger with the engine's cooling and lubrication systems. A mathematician fresh from Oxford, no matter how clever with differential equations, could hardly be expected to improve on years of practical engineering experience. But Hooker possessed a quality that transcended either mathematical brilliance or mechanical expertise. He refused to accept that existing solutions represented the limit of what was possible. If the test curves showed inefficiency, then the system could be improved. If the intake geometry created turbulence, then the geometry could be redesigned. The constraints were real, certainly, but constraints defined boundaries to work within, not reasons to stop trying. Over the following months, Hooker conducted a series of experiments to quantify the pressure losses in the Merlin's supercharger intake. He redesigned the intake elbow to smooth the airflow into the compressor eye, modified the rotor blades to better match the diffuser geometry, and developed a new supercharger casing that reduced turbulence. The improvements were individually modest, but combined they produced a remarkable 30% increase in supercharger efficiency. The engineering changes were incorporated into the Merlin 20 and later the Merlin 45, transforming the engine's altitude performance. The Merlin 45 powered the Spitfire Mark 5, which entered service in early 1941, with significantly better high-altitude performance than previous variants. For several months, the improved Spitfire held its own against the Messerschmitt 109F, the best fighter Germany had deployed to that point. The RAF's confidence in its equipment seemed justified. Then the Focke-Wulf 190 arrived, and everything changed. By late 1941, as British pilots struggled against the German fighters' brutal superiority, Hooker was already working on something far more ambitious than incremental improvements to existing superchargers. The Air Ministry had issued a request in early 1941 for an engine capable of high performance at 40,000 feet, initially intended for the Wellington Mark 6 high-altitude bomber. The specification called for power levels that no single-stage supercharger could achieve. The air at 40,000 feet was simply too thin for even the most efficient compressor to force enough oxygen into the engine cylinders. Hooker's solution violated conventional wisdom in multiple ways. Instead of one supercharger, he proposed two, mounted in series so that the first compressor fed compressed air to the second, which compressed it further before delivering it to the engine. The concept wasn't entirely new. American engines used turbochargers driven by exhaust gases to achieve two-stage compression, though with significant weight penalties and packaging challenges. But Hooker envisioned something different. Both compressors would be driven mechanically from the engine's crankshaft, mounted in a single compact assembly that would fit within the existing Merlin engine envelope. The engineering challenges were staggering. Each compressor would need its own impeller spinning at different speeds to optimize compression efficiency. The system would require a complex gear train to drive both impellers from a single input shaft. Most critically, compressing air generates enormous heat, and that heat reduces the density of the air being compressed, limiting how much additional oxygen reaches the engine cylinders. Hooker would need an intercooler, a heat exchanger mounted between the two compressor stages, to cool the air after the first stage of compression. The intercooler presented perhaps the most difficult design problem. Conventional intercoolers used air flowing over cooling fins to dissipate heat, but an air-to-air intercooler large enough to cool the highly compressed air from the first supercharger stage simply wouldn't fit in the Spitfire's compact airframe. Hooker instead designed a liquid-cooled intercooler, using a mixture of water and ethylene glycol as the cooling medium. The intercooler sat on top of the supercharger casing, a compact assembly that added minimal length to the engine while providing the cooling capacity needed to make two-stage compression practical. The first prototype, two-stage Merlin, designated the Merlin 60, ran on the test stand in March 1941. The power figures were extraordinary. At 30,000 feet, where the single-stage Merlin 45 produced barely 1,000 horsepower, the two-stage Merlin 60 generated 1,565 horsepower. The engine maintained that power output up through 25,000 900 feet, altitudes where conventional fighters could barely fly, let alone fight. But the Merlin 60 had been designed for bombers, and the Wellington 6 bomber program that prompted its development had been largely cancelled. Only 63 examples of the pressurized bomber were ever built. The revolutionary engine that Hooker had created seemed destined for obscurity, a brilliant solution to a problem that no longer existed. Then, the Focke-Wulf 190 crisis forced a desperate reassessment of priorities. In September 1941, an experimental Spitfire designated N3297 had been converted by Rolls-Royce at their Hucknall facility to accept a Merlin 60 engine. The aircraft was actually the sole Spitfire Mark III prototype, built with a strengthened airframe intended for future high-powered variants, but never put into production. Test pilot Geoffrey Quill flew the modified Spitfire and reported that the performance increase was a quantum leap over the Mark V, a transformation so dramatic it seemed to represent an entirely new generation of fighter aircraft. The problem was time. Supermarine was already working on a new airframe specifically designed for the two-stage Merlin, with improved cooling systems, strengthened structure, and modified aerodynamics. This aircraft, designated the Spitfire Mark 8, promised to be the definitive high-altitude fighter Britain needed. But getting the Mark 8 into production would require at least a year, possibly longer. Fighter Command didn't have a year. They needed something immediately, something that could contest the Focke-Wulf 190 before German air superiority over France became insurmountable. The solution was obvious but technically challenging. Fit the two-stage Merlin 61 into existing Spitfire Mark V airframes with minimal modifications. Create an interim fighter that combined the proven reliability of the Mark V design with the revolutionary power of Hooker's two-stage supercharger. The engineering challenges were substantial. The Merlin 61 was longer than the single-stage Merlin 45, requiring modifications to the engine mount and cowling. The intercooler and its associated cooling system needed integration with the aircraft's existing radiator installation. The propeller reduction gear required changes to accommodate the engine's higher power output, but these were problems that could be solved in weeks rather than months. In February 1942, the first true Spitfire Mark 9 prototype flew, using a converted Mark 5C airframe designated AB505. The Air Fighting Development Unit tested the aircraft in April and issued a report that was simultaneously cautious and enthusiastic. The performance of the Spitfire 9 is outstandingly better than the Spitfire 5, especially at heights above 20,000 feet, the report concluded. But it also noted handling quirks and systems integration issues that would need resolution before the aircraft entered service. The Air Ministry made the critical decision in May 1942. The Spitfire Mark 9 would enter immediate production as an interim type, bridging the gap until the purpose-designed Mark 8 could enter service. The first production aircraft rolled off the assembly line at Supermarine's Castle Bromwich facility in June 1942. Number 64 Squadron at Hornchurch received the first operational examples in July, just 13 months after the Focke-Wulf 190 had first appeared over France. The Spitfire Mark 9's first combat mission came on July 28, 1942. 12 of the new fighters flew a rodeo sweep, a fighter mission over enemy territory designed to draw German fighters into combat. The mission targeted Le Havre, and as the Spitfires crossed the French coast at 20,000 feet, they encountered 9 Focke-Wulf 190s. The German pilots had grown accustomed to fighting Spitfire Mark 5s, dictating combat terms through superior speed and climb rate. They initiated their standard bounce attack, diving from altitude to gain speed before pulling up into a climb that no Mark 5 could follow. But these weren't Mark 5s. As the Focke-Wulfs pulled up, expecting to climb away from their opponents with ease, the Spitfire Mark 9s followed them effortlessly. The British fighters maintained formation through climbs that should have left them wallowing and struggling, matching the German aircraft's every maneuver with authority that seemed impossible. Flight Lieutenant Donald Kingcome, leading the formation, destroyed one Focke-Wulf in the initial engagement. But more importantly, the German pilots broke off combat and retreated, unable to use their superior performance to control the battle. For the first time since August 1941, RAF fighters had met the Butcherbird on equal terms. The intelligence reports filtering back to Luftwaffe headquarters initially dismissed the engagement as pilot error or combat confusion. The Spitfire's performance couldn't have improved so dramatically so quickly, but as more encounters occurred throughout August, the pattern became undeniable. The RAF had fielded a new fighter variant that matched or exceeded the Focke-Wulf 190's capabilities at most altitudes and significantly outperformed it above 20,000 feet. On September 12, 1942, the highest air battle of World War II demonstrated just how completely Hooker's two-stage supercharger had transformed British fighter capability. Flying Officer Galitzine in his stripped-down Spitfire Mark 9 intercepted the Junkers Ju 86R at 41,000 feet above Southampton, pursuing the German bomber through altitudes where the air was so thin that both pilots fought against hypoxia and instrument freezing. The combat reached 43,000 feet before the German pilot, Lieutenant Erich Sommer, finally escaped with minor damage to his aircraft. The engagement proved that British fighters could now operate at altitudes previously considered safe havens for German reconnaissance and bombing missions. The Luftwaffe immediately cancelled all high-altitude raids over Britain, recognizing that Spitfires powered by two-stage supercharged engines had eliminated the altitude advantage that made such missions survivable. But the true measure of the Spitfire Mark 9's impact came in the grinding combat over France and the Low Countries during late 1942 and into 1943. The balance of air superiority shifted back toward the RAF as more squadrons converted to the new variant. German pilots who had grown confident hunting Spitfire Mark 5s now faced fighters that could climb as fast, fly as high, and in many cases outperform their Focke-Wulf 190s above 20,000 feet. The statistical evidence was overwhelming. RAF squadrons equipped with Spitfire Mark 9s reported kill-to-loss ratios approaching 3-to-1 against German fighters, a dramatic reversal from the dismal exchange rates of early 1942. More importantly, the RAF could resume offensive operations over Europe, supporting the strategic bombing campaign and preparing for the eventual invasion that would liberate Western Europe. Stanley Hooker's stupid obsession with mismatched impellers and inefficient intake geometry had accomplished something that conventional incremental improvements never could have achieved. By fundamentally rethinking how air entered and was compressed by aircraft superchargers, he had created an engine that transformed an obsolescent fighter design into the most produced Spitfire variant of the entire war. Over 5,600 Spitfire Mark 9s would eventually be built, serving on every major front where the RAF operated and remaining in frontline service until the war's end in 1945. The Merlin 61's two-stage supercharger incorporated design principles that extended far beyond World War II aviation. The mathematics Hooker developed for optimizing compressor efficiency became the foundation for modern turbine engine design, where multi-stage compression drives jet engines that power commercial aviation. Today, every turbofan engine in service traces its conceptual lineage back to Hooker's insight that properly matched compressor stages could multiply efficiency rather than simply adding their individual contributions. But in the autumn of 1942, as Spitfire Mark 9 squadrons began dominating the skies over Europe, such long-term implications seemed distant and abstract. What mattered was that British pilots were no longer being slaughtered by German fighters that they couldn't match. What mattered was that the balance of air power had shifted, and with it the possibility of eventual victory. The technical achievement that enabled the Spitfire Mark 9's transformation demanded engineering precision that pushed British manufacturing capabilities to their absolute limits. The two-stage supercharger system represented a conceptual breakthrough in fluid dynamics, but translating mathematical theory into functioning hardware required solving problems that had defeated conventional approaches for years. At the heart of Hooker's design lay a deceptively simple principle. Air entering the engine first passed through a moderate-speed compressor that increased its pressure by roughly 3-to-1. This compressed air then flowed through the liquid-cooled intercooler, which reduced its temperature from approximately 200 degrees Fahrenheit back down to ambient levels. The cooled, compressed air then entered the second compressor stage, which squeezed it to final pressures approaching 15 pounds per square inch above atmospheric. The compound effect meant that the engine received air at densities comparable to sea level conditions even at 30,000 feet, where the natural atmospheric pressure was less than 5 pounds per square inch. The intercooler represented perhaps Hooker's most innovative contribution to the entire system. Conventional wisdom suggested that cooling compressed air required large radiator-style heat exchangers mounted externally on the aircraft, adding enormous drag and weight penalties. American turbocharger systems used external intercoolers that consumed vast amounts of airframe volume and created installation nightmares for aircraft designers. Hooker instead developed a compact liquid-cooled intercooler that sat directly atop the supercharger assembly, using the engine's existing glycol cooling system to remove heat from the compressed air. The engineering elegance of the liquid intercooler extended beyond mere size advantages. By integrating the intercooler into the engine's cooling circuit, Hooker eliminated the need for separate cooling airflow paths that would have required extensive modifications to the Spitfire's carefully optimized aerodynamics. The intercooler matrix consisted of thin-walled brass tubes surrounded by cooling fins, with compressed air flowing through the tubes while glycol coolant circulated around them. The entire assembly weighed less than 60 pounds, a fraction of what an equivalent air-to-air intercooler would have required. Manufacturing the two-stage supercharger demanded precision that exceeded normal automotive engine tolerances by an order of magnitude. Each impeller had to be individually balanced to within half an ounce, requiring specialized equipment and skilled technicians who could detect and correct minute imperfections that would cause catastrophic vibrations at operational speeds approaching 20,000 revolutions per minute. The gear train that drove both impellers at different speeds required tooth-cutting accuracy normally reserved for precision instruments, with tolerances measured in thousandths of an inch. The intercooler matrix presented its own manufacturing challenges. Brazing the thin-walled brass tubes to their aluminum housings without creating leaks or structural weaknesses demanded temperature control and metallurgical expertise that pushed British manufacturing capabilities. Each intercooler required careful, leak testing under pressure before installation, and even minor imperfections could compromise the entire system's effectiveness. Production facilities at Rolls-Royce worked around the clock to manufacture sufficient components to meet the desperate demand for two-stage Merlin engines. As production of the Spitfire Mark 9 accelerated through late 1942 and into 1943, the strategic impact of Hooker's supercharger innovation became increasingly evident. RAF squadrons equipped with the new variant reported dramatic shifts in combat effectiveness that went far beyond simple performance statistics. The psychological dimension of air combat had fundamentally changed. German pilots who had grown accustomed to dictating engagement terms through superior altitude performance now faced British fighters that could match or exceed their climb rates and operate effectively at altitudes previously considered safe havens. Flight Lieutenant John Checketts of 611 Squadron accumulated 13 confirmed victories while flying Spitfire Mark 9 EN 572 between April and September 1943. His combat reports detailed engagements that would have been impossible with earlier Spitfire variants. On July 17th, Checketts intercepted a formation of Messerschmitt 109G fighters at 27,000 feet over northern France. The German pilots attempted their standard tactic of climbing above the Spitfires to gain altitude advantage before attacking. Checketts followed them effortlessly to 32,000 feet, maintaining enough energy reserve to engage in turning combat at an altitude where earlier Spitfires would have been helplessly slow and vulnerable. The combat effectiveness of the Mark 9 was reflected in casualty statistics that told a story of dramatic reversal. During July and August 1942, before the Mark 9 entered widespread service, Fighter Command's Spitfire squadrons achieved kill-to-loss ratios, averaging 1.3 to 1 against German fighters. By December 1942, with Mark 9s constituting roughly 30% of frontline strength, the ratio had improved to 2.7 to 1. By mid-1943, when most frontline squadrons had converted to Mark 9s, the ratio exceeded 4 to 1 in favor of RAF fighters. The Mark 9's versatility extended far beyond air superiority missions. The aircraft proved equally effective as a fighter bomber, carrying one 500-pound bomb and two 250-pound bombs on underwing racks. The two-stage superchargers' improved altitude performance meant that fighter bomber variants could climb to 25,000 feet with full bomb loads, operating above the effective range of most German light anti-aircraft weapons. Tactical reconnaissance variants used the Merlin 61's power to photograph enemy positions while flying at speeds and altitudes that made interception extremely difficult. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The photo reconnaissance role revealed another dimension of the two-stage supercharger's impact on RAF operations. The PR Mark 11 Spitfire, essentially a Mark 9 airframe with cameras replacing guns and armor, could cruise at 35,000 feet while photographing targets across occupied Europe. The combination of high speed and extreme altitude made these aircraft nearly invulnerable to German interceptors. During 1943, PR Mark 11s flew thousands of sorties over heavily defended targets, providing intelligence that proved crucial for planning bomber raids and eventual invasion operations. Loss rates for these reconnaissance missions dropped to less than 1%, a remarkable achievement given the dangerous nature of deep penetration flights over enemy territory. The German response to the Mark 9's appearance revealed how completely Hooker's supercharger had disrupted Luftwaffe tactical doctrine. Intelligence reports captured after the war showed that German fighter commanders issued desperate instructions to avoid combat with Spitfires at altitudes above 20,000 feet unless holding decisive numerical or positional advantage. The Focke-Wulf 190's superiority had evaporated, replaced by reluctant acknowledgement that British fighters now held the advantage in the vertical dimension where modern air combat was decided. Oberstleutnant Adolf Galland, commanding Luftwaffe fighter forces in Western Europe, recognized the strategic implications immediately. His reports to Berlin in late 1942 warned that the improved Spitfire represented a decisive shift in the air balance over occupied Europe. Galland requested immediate deployment of Germany's newest fighters, including the Messerschmitt 109G and improved Focke-Wulf 190A4 variants, but even these aircraft struggled to match the Mark 9's high-altitude performance. The fundamental problem was that German engines lacked equivalent two-stage supercharging systems, and developing such technology would require years of research and manufacturing infrastructure that Germany increasingly could not afford. The production statistics told their own story of the Mark 9's importance to Allied air strategy. Between June 1942 and June 1945, British factories manufactured 5,656 Spitfire Mark 9s, making it the second most produced variant after the Mark V. The aircraft served on every major front where RAF squadrons operated. Two tactical air forces preparing for the invasion of Europe included Mark 9 squadrons as their primary fighter component. Mediterranean squadrons flew Mark 9s in support of operations in Sicily and Italy. Even Far Eastern squadrons eventually received Mark 9s, though the aircraft's limited range and tropical cooling challenges meant it never achieved the same dominance against Japanese forces. American fighter groups operating in the Mediterranean theater also flew Spitfire Mark 9s before transitioning to P-51 Mustangs in early 1944. The 31st Fighter Group accumulated over 400 victories while flying Mark 9s, with several pilots achieving ace status in the British fighter. Lieutenant Richard Hurd scored 6 victories in Mark 9s between January and March 1944, becoming one of the highest-scoring American pilots flying British aircraft. These American squadrons provided valuable feedback on the Mark 9's combat characteristics, generally praising its handling and high-altitude performance, while noting that its limited range restricted operations to relatively short-range escort missions. The Mark 9's combat record included several notable achievements that demonstrated the aircraft's exceptional capabilities. On October 5, 1944, Spitfire Mark 9s of 401 Squadron became the first Allied fighters to shoot down a Messerschmitt 262 jet aircraft. The engagement occurred near Nijmegen in the Netherlands, where Flight Lieutenant Robert Cole managed to position his Mark 9 to intercept an Me-262 during its landing approach, exploiting the jet's vulnerability when flying slowly with landing gear extended. The victory demonstrated that even the latest German technology couldn't guarantee invulnerability against well-flown conventional fighters with superior altitude performance. The highest combat engagement of World War II, Galitzine's September 12, 1942 interception of the Junkers Ju-86R at 43,000 feet, revealed both the Mark 9's extraordinary capabilities and the desperate measures taken to achieve them. Galitzine's aircraft had been stripped of all non-essential equipment, including armor plating, most of its ammunition, and even the radio. The weight reduction allowed the aircraft to climb above 40,000 feet, altitudes where both pilot and machine operated at the absolute edge of survivability. The engagement proved that British fighters could reach any altitude German aircraft could achieve, eliminating the last refuge for Luftwaffe reconnaissance and bomber operations. The technical evolution of the Mark 9 continued throughout its production run as Rolls-Royce refined the two-stage supercharger system. The original Merlin 61 gave way to the Merlin 63 in early 1943, incorporating improved intercooling and higher boost pressures that increased power output to 1,700 horsepower at 25,900 feet. The low-altitude optimized Merlin 66 powered the LF Mark 9 variant, which became the most numerous version with over 4,000 produced. This variant traded some high-altitude performance for increased power below 20,000 feet, making it particularly effective as a fighter-bomber and tactical fighter supporting ground operations. The HF Mark 9, powered by the specialized high-altitude Merlin 70, represented the ultimate development of Hooker's two-stage supercharger concept. This engine maintained full power up to 30,000 feet, with usable performance extending past 40,000 feet. Only 410 HF Mark 9s were manufactured, reflecting the specialized nature of their high-altitude interception role, But these aircraft provided crucial capability for defending Britain against German reconnaissance aircraft and potential high-altitude bomber threats that never fully materialized. By 1944, as Allied forces prepared for the invasion of Europe, the Spitfire Mark 9 had become Fighter Command's standard equipment. Nearly all frontline squadrons flew Mark 9s in various configurations, from pure fighters to fighter bombers to tactical reconnaissance variants. The versatility that Hooker's two-stage supercharger enabled meant that a single basic airframe could fulfill multiple roles, simplifying logistics and training while providing commanders with flexible tactical options. The D-Day invasion on June 6, 1944, showcased the Mark 9's complete dominance of European skies. Allied air forces flew over 14,000 sorties that day, with Spitfire Mark 9s constituting a substantial portion of the fighter component. German air opposition was minimal, reflecting the Luftwaffe's recognition that contesting Allied air superiority over the invasion beaches would result in catastrophic losses. The few German fighters that did engage Allied forces found themselves outnumbered and outperformed by Mark 9s operating at peak effectiveness across all altitude ranges. The psychological impact of the Mark 9's superiority extended beyond tactical considerations to affect German pilot morale and training. Luftwaffe fighter schools in late 1943 began emphasizing defensive tactics and survival techniques rather than the aggressive engagement doctrines that had characterized earlier training programs. German pilots learned to avoid combat unless holding decisive advantages, to disengage immediately when facing superior opposition, and to prioritize survival over achieving victories. The transformation from offensive confidence to defensive caution reflected the Mark 9's role in establishing Allied air superiority over Europe. Stanley Hooker never flew in combat, never experienced the life-or-death struggles where his two-stage supercharger made the difference between survival and death for thousands of Allied pilots. His contribution came from mathematics and fluid dynamics, from understanding how air behaved when compressed and cooled, from recognizing that conventional solutions weren't sufficient for the challenges modern warfare demanded. The 30% efficiency improvement he achieved with the original Merlin supercharger had been impressive. The two-stage system he developed represented a quantum leap that fundamentally altered the strategic balance of the air war. The broader implications of Hooker's work extended far beyond the Spitfire program. The same two-stage Merlin 61 that powered the Mark 9 was fitted to the North American P-51 Mustang, transforming an excellent low-altitude fighter into the long-range escort that made strategic bombing of Germany possible. The liquid-cooled intercooler concept that Hooker pioneered became standard practice for high-performance piston engines, appearing in various forms on American, German, and Soviet aircraft throughout the war's final years. Post-war analysis by American and British technical intelligence teams studying German aircraft development revealed how completely the two-stage supercharger had disrupted enemy planning. German engineers had recognized the potential of two-stage compression early in the war, but manufacturing complexity and material shortages prevented successful implementation. Several experimental German engines incorporated two-stage systems, but none achieved the reliability and production readiness that Hooker's Merlin 61 demonstrated. The technical gap wasn't a matter of theoretical understanding. German engineers knew what needed to be done. It was a matter of practical implementation, of solving the thousand small problems that separated concept from reality. The mathematics that Hooker developed for predicting compressor performance under varying atmospheric conditions became the foundation for modern turbine engine design. Every jet engine relies on multi-stage compression, with each stage carefully optimized to work in harmony with those before and after it. The principles Hooker established while struggling to make the Merlin supercharger more efficient directly enabled the jet age that followed. His later career at Bristol Aero Engines, where he designed the Olympus turbojet that powered both the Vulcan bomber and eventually Concorde, demonstrated how completely his understanding of compression aerodynamics translated from piston engines to turbines. The Spitfire Mark 9 remained in frontline service until the war's end, even after the appearance of the Griffon-powered Mark 14 and other later variants. The Mark 9's combination of proven reliability, excellent handling characteristics, and sufficient performance to compete with any German fighter made it the preferred mount for many experienced pilots who valued familiarity over marginal improvements in raw performance. Several RAF squadrons flew Mark 9s into the final weeks of the war, supporting ground operations in Germany and providing air cover for the final collapse of Nazi resistance. The post-war fate of Spitfire Mark 9s reflected their status as surplus equipment in an age that had moved beyond piston-engine fighters. Many were sold to foreign air forces seeking modern equipment at affordable prices. The Belgian, French, Israeli, and Egyptian air forces all operated Mark 9s during the late 1940s and early 1950s. Some saw combat in regional conflicts, proving that even aging piston fighters retained value against less sophisticated opponents. The Israeli Air Force flew Mark 9s during the 1948 Arab-Israeli War, achieving air superiority over Egyptian and Syrian forces, flying a mix of British and German surplus aircraft. As jets replaced piston fighters throughout the 1950s, surviving Mark 9s gradually transitioned to training roles, gate guards, and eventually museum preservation. Today, roughly 60 Spitfires of all variants remain airworthy, with Mark 9s constituting a significant portion of flying examples. These aircraft serve as living reminders of an era when air combat depended on pilot skill, aircraft handling, and the invisible mathematics of supercharger efficiency that determined who held the altitude advantage in life or death encounters. The story of Stanley Hooker's two-stage supercharger and the Spitfire Mark 9 it enabled represents more than just technical achievement. It demonstrates how individual innovation can alter the trajectory of warfare when combined with institutional support and manufacturing capability. Hooker's freedom to explore unconventional solutions, granted by Ernest Hives in 1938, enabled the mathematical analysis that revealed efficiency improvements others had missed. The Air Ministry's willingness to fund development of the two-stage Merlin, initially for a cancelled bomber program, created the technology that would save the fighter force. Supermarine's decision to adapt existing airframes, rather than waiting for purpose-designed variants, got revolutionary capability into combat months ahead of schedule. The convergence of these factors, mathematical insight, manufacturing precision, institutional flexibility, and operational urgency, transformed a crisis of German air superiority into Allied dominance that helped ensure victory in Europe. The Focke-Wulf 190 that had threatened to make RAF fighter operations untenable became just another aircraft that British pilots could engage on equal or better terms. The altitude advantage that Luftwaffe fighters had exploited since the war's beginning evaporated, replaced by British fighters that could climb faster, fly higher, and fight more effectively than German aircraft designed specifically for high-altitude combat. Stanley Hooker's autobiography, published shortly before his death in 1984, carried the self-deprecating title, Not Much of an Engineer, referencing Ernest Hives's reaction to discovering that his new hire held mathematical, rather than engineering, qualifications. The title captured Hooker's characteristic modesty, but it belied the reality of his contributions to aviation history. The engineer, who wasn't much of an engineer, had designed superchargers that powered the Spitfire, Hurricane, Lancaster bomber, and Mosquito. He had developed the Welland and Derwent engines that powered Britain's first operational jet fighter. He had created the Olympus turbojet and the Pegasus vectored thrust turbofan that enabled the Harrier jump jet. He had saved Rolls-Royce from bankruptcy in 1971 by rescuing the troubled RB211 program. But perhaps his most significant achievement remained that elegant solution to an impossible problem in early 1941. Two compressors working in series, separated by a compact liquid-cooled intercooler, mounted in an engine package that fit existing airframes with minimal modifications. The stupid obsession with mismatched impellers and inefficient intake geometry that had transformed into a weapon system that changed the course of the air war over Europe. The final measure of Hooker's success came not from official reports or casualty statistics, but from the pilots who flew aircraft powered by his engines. Geoffrey Quill, Supermarine's chief test pilot, who flew the first two-stage Merlin installation, described the performance increase as a revelation that transformed the Spitfire from a good fighter into a great one. Donald Kingham, who led the first combat mission with Mark 9s, reported that the aircraft felt like it belonged to a different generation entirely. The thousands of Allied pilots who survived the war flying Spitfire Mark 9s owed their lives to many factors, but Stanley Hooker's two-stage supercharger ranked high among them. As the autumn of 1945 brought peace to Europe, the Spitfire Mark 9 that had dominated the skies for 3 years began its transition to obsolescence. Jets were the future, and piston engines, no matter how sophisticated, represented the past. But the principles that Hooker had established, that proper matching of compressor stages could multiply efficiency, that liquid cooling could solve packaging problems, that mathematical analysis could reveal solutions invisible to intuitive mechanical understanding, these principles endured. Every modern turbine engine embodies Hooker's insights. Every aircraft that flies at high altitude benefits from compression technology that traces its lineage to his work at Rolls-Royce between 1938 and 1941. The engineer's stupid idea, dismissed by colleagues who understood the conventional limits of supercharger design, had proven that sometimes the most revolutionary solutions come from refusing to accept that current limitations define future possibilities. Hooker looked at test curves and saw inefficiency where others saw acceptable performance. He envisioned two-stage compression where others saw unnecessary complexity. He designed liquid cooling where others insisted on air-cooled systems, and in doing so, he gave Britain the weapon it desperately needed, precisely when it was needed most. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.